Hello and welcome to part 11 of Dev Maths and Stats Refresher Course, Lecture 5. Before the final part of the lecture looking at optimization with inequality constraints, just want to point you to a few of these wonderful visualizations in the Wakelet collection that are really good illustrations of the Lagrangian principle and how that works. It might help you remember that. Here's the simplest one in 2 dimensions, although it's referring to a 3-dimensional graph. So this green graph is the contour map of this function, x squared plus y squared. So it starts at 0, because when x and y are 0, the function is 0. As x and y increase, it becomes larger and larger, and it's symmetrically. So in any cross section, it would be like a parabola, y equals x squared. It's 3-dimensional. So you're trying to find the minimum value of that, but the minimum unconstrained value is here. But you're given this constraint, you must be on this curve here, which is the y squared minus x is 5, or in other words, x is y squared minus 5. So it's a parabola like this. So where on this curve can you find the minimum points of this function? And as well as the curves, I've drawn here 2 lines. This line is the gradient function of the gradient vector of the main function, the green function, the objective function. And this line is the gradient function of the gradient vector of the constraint. So from this point here, if I move further along the constraint in this direction, if I take this is my direction I'm moving, dx dy, the dot product of this with the constraint function will be 0 because it's at right angles. It must be at right angles because it must be 0 because I'm not changing the constraints, I'm staying on the constraint line. So the constraint stays at 5, that's the rule I have to follow. So if I move in this direction, that dot product must be 0, so this must be 90 degrees. However, if I go in this direction, you should be able to see that the function is decreasing. I'm moving down in towards this valley area here. And that's because this vector dotted with this vector will give me a negative answer because it's an obtuse angle. Whereas when I come to here, again, if I move along the constraint function, still this is 90 degrees, so the constraint is still 5, but at this point, the function is increasing because it's an acute angle here. So the best point I can get to is back here. And now, if I move in any direction along the constraint, the change in the function is now 0, which means that my movement must be at right angles to the red gradient function, but also it still must be at right angles to the blue one, which means that both the blue and the red have to coincide at the optimum points. So now you can just see where the optimum points are. They're there and there. Oops. Somewhere here. Yeah, and there's another one around here. Where they're all aligned. Like, I can't get that one to work. Oh, there. Okay, like that. Yeah. So those are the 3 optimum points. So what Lagrange does is it says that where these are snapping onto each other exactly, then the 2 vectors must be a multiple of each other. And that's how the Lagrangian method is derived, or that's the principle on which it works. Okay, so much for that 2-dimensional one. Now, more exciting looking 3-dimensional one. Again, here all you've got is this is the actual function in 3D. So it's going up. So again, you're looking for a minimum and maximum points, both minimum and maximum points on this particular curve. So the curve is slightly more complicated this time. You can move anywhere around there, and we can decide where it's going to be. You can see here, again, it's got the 2. This is the oops, shame they didn't color code the arrows, but you can tell. You should be able to tell which one is which. One of them is the gradient vector of the constraint. One of them is the gradient vector of the original function. And this one's the original function. This one's the constraint. And the extrema, the maximum and minimum values will be where they line up, which I don't think they have, like there and there. So again, it's where they're parallel. And you can see, it's quite nice, you can see over on the actual drawing of the graph, that's where it occurs at this point. And again, at this point, so you can see this moving around the curve. matching up to these four, the two maximums and the two minimums occur at these points here when the two gradient vectors are lined up or parallel. So again, Lagrange multiplier will find that. And finally, this one's the one I like most of all because it's such a nice complicated graph. And here again, you're moving around on this grey space to show the combinations of x and y. And then here it shows you the value of the function, which is quite a complicated looking function. These are the only values you can actually take because you're on the constraint. As you move around here, this is the gradient function of the constraint. So you're always moving at right angles to that. This is the gradient function this is the gradient vector of the function. So this red one it's the dot product, or the dot product of the direction you're moving along the constraint and this blue vector, which is showing you how much the function is changing. So, because the red one's quite small, so it shows it's not changing very much as I move along here. It's just slightly increasing. And here, it's showing as I move down here, it's slightly decreasing, so I'm going down the hill. Because the direction I'm going in, this direction, dots with this, is they're going in opposite directions, so that must be negative. It doesn't show the dot product with this one because that's always 0. So when I get to a point along here where I can't increase or decrease this anymore, then the dot product of this line I'm moving on and this becomes 0. In other words, this line must be at right angles to this one. It's already at right angles to this one, so the blue and the green must match up, must be parallel at those points. So you can see there's one there. That's that maximum point. Keep going around. So there's one there. So there's one there. This is an example of where they're actually pointing in opposite directions. They're still lined up. There's still a multiple. So that's this one. Another one probably here. And that maybe another one down at the bottom there. Yeah. And that shows another one up there, surely. About there, up here. So again, all the places where you have a maximum or a minimum, the gradient vectors of the constraints and the objective function will be parallel, which means there must be a multiple of each other. So the Lagrange multiplier method will find out all of those. Now, without having to visualize this incredibly complicated shape, just from the equations, you can work out when these two things are parallel, and that will find the constraint optimums, or the constraint maximum and minimum. Okay, so the final lecture I'll go on to talking about inequality constraints, which really just puts together the previous two sections in a sort of systematic way. But for now, thanks for watching.